So, we're back again. I'm in my hot ass room in Thailand, no AC. Got to keep the fan off so you guys can hear me. So, back with our series on building foundational machine learning models from scratch in PyTorch. Well, in PyTorch, I guess, as from scratch as that's going to be in PyTorch. But this way, you really get to learn what it means to manipulate tensors, and when you build up your foundational knowledge of these different models, you'll really start to be able to create different things. So the goal is to eventually build a diffusion model, image diffusion model, and so a multimodal model, and maybe trying to use an LLM as the encoder, as the text encoder. So yesterday, right? So we started with a language transformer, building a language transformer based on Karpathy's video, and then we repurposed it to a vision transformer, and then we got good validation accuracy on MNIST, and then we tried it with CFAR10, and that's a more complex data set, although in the grand scheme of things, not too complex. But we scaled it up using RunPod, and I said I wanted to get somewhere around 85% validation accuracy. We started out, we ended up getting, the model ended up overfitting around 60 something, 65% validation accuracy. So I added a learning rate scheduler, I increased the dropout, and I did something else. I don't remember. After doing that, all right, I added more data augmentation, like random horizontal flips, rotations. After doing that, we got a little bit higher validation accuracy, around approaching 70%. But then we ran into the problem of exploding gradients. So I added gradient clipping, and then I let it train for longer, and I ended up with around upper 70%, like 78% validation accuracy. And then I said, okay, well, I'm sure there's more we can do, but for now, what if we were to use a model, foundational machine learning model that we know does well for the task of image classification, like ResNet18, because we know that vision transformers are data hungry, and for a more simplistic data set and task like classification on CFAR10, it'll be a lot easier for a transformer model to overfit. So it's not that we can't get 85% accuracy. I know that we can, but how about we take a step back and try ResNet18? Of course, obviously, this isn't like the most orthodox experimental approach, right? Like, I'm going with my curiosity now. I'm building things going with my curiosity. I don't really care about, oh, well, we should have done ResNet first and built a different kind of baseline. I don't care about that. To an extent I do, but not to the extent that it dampens my curiosity. So we're going to build ResNet18 from scratch in PyTorch. The reason being, ResNet18 is because it uses stacked convolutional feature extractors. It is more suited. It is more suited. It's more suited in a. It's more suited in a non-complex way to the task of image classification. And it does, and because the model has inductive bias, which inductive bias isn't a bad thing, but vision transformers, because they don't have inductive bias, which means they don't really make any assumptions about the data, which means they are translation invariant, they are more data hungry, right? You can sort of think of it. I think that is a good principle in general. The less assumptions you make, the less assumptions your model architecture makes about your data, the more data hungry it's going to be. Convolutional neural network based models that have these, stacked subsequent convolutional layers or feature extractors make assumptions about your data. They have inductive bias. That means that your convolution, your kernels, your convolutions, aka your kernels, make a spatial assumption. They say that elements in your image that are more close in space are going to be more related to each other. And then the model trains and builds around that assumption and uses the strength of that assumption to increase its predictive power, right? It's not a bad thing. It's just that for other tasks, that assumption might hurt the performance. For instance, you know, image to text, right? Take this image and describe what's in it in English. Vision transformers are going to be much better at that because they don't, for the same reason that language transformers are good for language. Like, how do we model long distance relationships between subject and object, or words in a sentence, right? Just because a word comes here, yes, it's likely that the words around it are related to that word in terms of structure, in terms of what it means semantically, but there are also long range dependencies. We can also have a word here, a bunch of words in between it, but then this word will be strongly related to the word in the future, right? A model with a lot of inductive, and same thing with an image. We could have some part of the image here and be very strongly related to a part of the image here, which could make up the entire theme of the image. Maybe this is in the background, maybe this is in the foreground, and they're communicating with each other, but that's the entire point of the image, right? So a vision transformer, which doesn't make any assumptions about your data, right? Which just uses self-attention, which is, it's dot product. It's taking the dot product of the patch embedding with itself, which is a translation invariant operation, is going to perform much better for a task like image to text, or any type of model or system architecture that needs to model long-range dependencies. And it's going to do that better than a recurrent neural network. Recurrent neural networks were our first attempt at modeling long-range dependencies, but it's like a very it's an incredible architecture, but it's not nearly as elegant as self-attention, right? It's very explicit. It's like, we're going to model long-range dependencies and do it with this like very heavy, bulky architecture where self-attention is, and it's extremely elegant, right? So anyways, we're going to use ResNet18, which is a model that has inductive bias, which is probably gonna perform well on our classification test. We know that it does. There are papers that are published that say that it does. But my theory is that it's going to converge quicker than a vision transformer. It's going to converge to a better validation accuracy than a vision transformer. So in this video, I'm going to implement the foundational pieces of ResNet18, which is the 2D convolutional layer, 2D max pool layer, 2D average pool layer, which are all very similar, and I could probably use polymorphism, but I'm going to implement them separately. So yeah, let's get started. I actually just got out of the spa. I did a cold plunge for 5 minutes, held my breath for a minute. Probably gonna do a swim in the ocean later, 1,000 meters before I do jujitsu. Been training with Owen Lipsy recently. He's been kicking my ass, but I've been learning a lot from him. Anyways, let's get started. So I actually made this video earlier, but something went wrong with the recording, so I literally recorded like an hour's worth of content and it didn't capture anything that I did. So I have the files and everything. I'm just gonna delete them and just literally do it over. But anything for you guys. So let's torch. As always, I type everything out. It's like drilling in jiu-jitsu for muscle memory. We are going to type everything out. So let's start with implementing 2D convolution. So we'll do the main function. Hopefully I can do this before it hits the peak of the heat and I start sweating out my soul. I should antagonize that a little bit by drinking coffee because I'm an addict. Okay. Now that I'm properly stimulated, let's test test modules. We'll pass in a config, which means we need a data class as always. I don't know what we need in there yet, but module name, let's just write the skeleton for the test first. Module name, myconv 2D. And then of course it's going to subclass. And then module starting to sweat. Module and then the acronym I use is IOKSP. That's input in channels, out channels, kernel size, stride, P. And then you always gonna want to remember this equation as well. The dimensions of something coming out of a a convolution operation is hn plus 2p minus k integer division plus 1 inchan c in c out kernel stride padding. So the constructor, what do we need? Wait, init, kernel, yeah, let's move this down here. Oh my goodness, can't type. In channels, out channels, kernel, size, stride, padding. So, Let's pause the video. There's actually some noise, so I had to close my door. You can probably still hear it, but I'm committed to getting this done right now, so let's just power through. Okay, so let's see. Where were we? So self dot in channels, self dot out channels, receives out channels, kernel size, stride, wait, init, scale. And then we're going to self.weights is going to be, and then these are going to be our trainable parameters. And we're going to initialize them using a standard normal. And then we're going to scale by weight init scale. This is so we prevent the gradients from exploding, prevent numerical instability, and from numbers growing too large during training, just too quickly. Just want to scale those back. There are always like more optimal ways to initialize your parameters, but you'll find that just for the sake of these educational videos, I'm gonna initialize parameters with a random normal, and then we'll go back and make changes and talk about why we want to initialize things differently, like Xavier initialization and stuff like that. So, right, this is going to have shape C out, C in. So out channels, in channels, K, kernel size, kernel size. So out channels, in channels, kernel size, kernel size. Just so it's all on the same line. Okay, wait. Okay. So yes, this is right. Okay, so now forward. So let's actually just get the skeleton working in tensor. Say batch size 6. We're gonna pass in an image batch, like training data, right? Like batch size 6, channel dimension 3. We're using CFR10, so we'll do channel dimension 3, and then 32 by 32. And then what's gonna change is when we pass it to the convolution, especially when we say, right, kernel size. Out channels, specifically out channels. If we say 20, then we expect a 20 dimensional, we expect dimension after the batch dimension to be size 20. So that means we're defining 20 kernels or 20 feature maps. Stride 1 padding, we'll use same padding, which means if kernel is 3, then padding will need to be 1. So wherever the kernel is centered on, you'll need the number of pixels on either side. So if it's 3, that means that this is the center of the kernel. We'll need to pad by 1 in order for the image to remain the same when it goes through the convolution operation. Again, all of this is going to be much easier to show you and illustrate once I have the capture card and I can use my iPad. So in tensor, this is a torch dot zeros. What are we gonna do random? Out tensor module in tensor, and then assert, and then expected shape is 6, 20, 32, 32. Assert that out tensor dot shape equals expected shape. And if it doesn't, we'll print failed expected but got boom. And let's just put the out tensor shape. So let's run this. Line 8. We need to create the config, pass it in here. Oh. In channels, weight, init, scale. Right. In channels 3. Weight. Oh. Weight, init, scale. Weight, init, scale. What line is this? 26. Weight, init, scale. Oh. Right, I need to call the super class constructor. Right. Failed, but got, right, because we just returned exactly what was passed in, which is going to be of shape. So in shape. Actually, I should copy this because I'm going to use this anyways. And then we want to return shape B, C out, X, H out, W out, where H out equals H in plus 2 times plus 2p minus k divided by s plus 1. So, all right, we're going to use torch.nn. So we imported it as f, but we're going to use torch.nn.functional.unfold. Remember, if you remember when we implemented patch embeddings, we used the torch.tensor object.unfold. This is different. This is, again, IOKSP, kernel size, stride, padding, KSP, X unfold. So this is where we're going to do the convolutional operation right here, using torch.nn.functional.unfold. And it takes in X, our input, kernel size, stride, padding is going to be, yep. And it's going to create a tensor of size B, Cn, K, B, Cn, K, K times L, where L is H out times W out. And so basically so the first dimension of the output is the batch dimension. And what this unfold does is it extracts patches. It runs your kernel over your tensor. And it does it for each channel. So if you have a three-dimensional input, it runs. If your input is one image with 3 dimensions, 1, 2, 3, then it extracts a k by k patch and unfolds it, and then it stacks each dimension on top of it. So one unfolded kernel stacked with another, right? And then you're going to perform some unit of operation on that dimension. The thing that's kind of confusing to me, which I don't know why they do it this way, is personally I think they should have the L dimension, so the first dimension and the second dimension switched. I personally think that the unfold operation should yield a L by Cn, because L is the number of extracted patches. It's just L is the number of extracted patches, and then Cn times K is essentially your stacked, the content of your stacked patches of your stack of the patches for each dimension. So let's just keep it simple and say we have one channel input. Then the content. So, and then let's say we have 16. We run our kernel over our tensor image, and we get 16 patches. Then L will be 16, right? So 8 by 8, it'll be 16. And then since it's one channel, for each patch, you'll have just the stacked kernel. So if your kernel is size 3, you have 3 times 3 is 9 pixels. So that'll be 9 pixels. But if you have 3 dimensions, then it'll be 9 times 3, 27. So it'll stack all of them in one, and so it'll have L patches, and for each patch you'll have 27 pixels. That makes a lot more sense to me personally. I don't know why. I think it probably has something to do with memory and how the tensor is organized contiguously in memory. But yeah, this is how it outputs it. B Cn times K and L. but we're going to transpose it anyways. So x unfold transpose equals x unfold dot transpose 1 2, and that gives us this. We have to do this to multiply it by our weight matrix. Right. So remember our weight matrix this is the shape C out C in K K. So we're gonna do self. We're gonna say weights equals self dot weights dot view C out. Wait, do I have C out? No, I don't. So I'm just gonna infer it by -1 because I have the rest of the dimensions. C in times K, right? Because I have K labeled up here and C in and K from here. Right, so this is going to give us C out, C in times K, right? And then I'm going to multiply X unfold. So I'm going to say out equals X unfold T, matrix multiplication, weights dot transpose, which is going to be C in K times C out. So this is basically B, L, C in K times K, times C in times K, C out, which yields B, L, C out. And then we're going to say out receives out dot view. Remember, we want shape. We want this to be the shape. So actually we need H out and W out. So H out equals, remember, height and width are the same for the kernel. So the equation for H out is going to be the same as the equation for W out. P minus K integer division plus 1. And then out dot view is B I'm gonna switch the dimensions and expand L in the same. I don't have C out, so I'm going to infer it, and then H out, W out, and then I'm gonna return out. I think this should work. Let's see if we have any errors. Python. Well, so before I do that, so basically what I'm doing is I'm extracting the patches. I'm running a kernel over our tensor, over our image, which is represented by a tensor, and I'm extracting. See, once I have my iPad, I will draw this out. You'll see very clearly what's happening. I'm extracting L number of patches, and then for each patch, I'm unfolding the kernel, I'm unfolding the pixels, I'm flattening the pixels in concatenating each dimension, so for the 3 dimensions. And then what I'm doing is when I'm multiplying by weights is I'm doing a dot product between the weights, the learnable weights, and the flattened pixels for each dimension. And what those learnable weights becomes are feature extractors or feature mappers, which we can say, oh, this is the nose feature mapper. So remember, dot product is just a similarity score. So if these weights learn to be something that can detect eyes, we'll say, okay, the 3 dimensions for this patch, when dot product with this eye feature extractor, if it yields a high score, then it's likely there's an eye located in this kernel, right? That's how it works. And that's what I mean. Implementing code really gets you. It's one thing to understand images. You want to understand the intuitive feel of writing out and looking at the image and the code. You want to really understand what the matrix multiplication is doing. Something weird's happening. Okay, there you go. I don't know why it was pausing the way it was. Let me make sure OBS is still working properly, because if I have to redo this code. Okay, cool. So let me run it one more time. Yeah, it looks like it's running without errors. I'm pretty sure our convolution operation is working properly. It looks complicated, but once you get it, it's pretty straightforward. I mean, it is complex. It's a complex thing to understand. It is. All right, let me not do it. I hate when people are like, "Oh, this stuff is easy." Yeah, everything's easy once you fucking get it. This is very challenging stuff, guys. And you have to practice a lot and think about it a lot for it to become intuitive. But it's very rewarding once it becomes intuitive. So let's move on. Let's move on with the rest of the video. Implement myconv 2D, max pool 2D. Average pool 2D. Max pool, wait, doesn't need this or this because it doesn't have weights. This only needs output size. My computer is running slowly for some reason. Yeah, my computer's running slowly. I don't know why. My laptop is running slowly. OBS is really taking up a lot. Interesting. Okay. Well, let's just move a little bit more. So max pool isn't going to really look much different than the convolution. It's going to use unfold. We're just not going to multiply by any weights. It has no weights. Neither max pool nor average pool have any weights. Class my average pool. tuple. All right, so let's go to max pool. No in channels or out channels. Out channels is gonna be whatever in channels is. Max pool is just going to extract the max number from a kernel. So we're gonna slide a kernel along a tensor and extract the max number for each of that kernel. So kernel size, SP stride padding, kernel size, getting hot in here. So X, it's going to be basically the same. It's very similar to what we did before. X dot or F dot unfold X kernel, actually, so B C N H N W N receives X dot shape, K S P receives self dot kernel size, self dot stride, self dot padding, K stride S padding P. This gives us, remember, B C N K K L, where L is equal to H out W out. X unfold. This time, instead of transposing, we're going to do a view where we do B C N K K and then L, which we don't have H out and W out, so we infer it. So B C N K K L, and then we're just going to say X max equals X unfold. Actually, I think it's, this is max pool, X max equals X unfold dot max dim equals 2. So the second dimension 0, 1, 2. We're going to take the max of this dimension, right? So this is going to remove the K, the second dimension, and reduce the tensor to CNL. And then we're going to say X out receives X max. And we do, we ignore this second return The second one is the the index of the max, and the first is the actual max, which is what we want. Dot view BCN. And I guess we need to H out equals HN plus 2 times P minus K integer division Okay, so max pool, we should get 3. Yes. Yes. So if we run this, computer's pretty slow, so let's just wait. Output size 127. Oh. Like in ResNet, it'll be 1-1, but we're not even doing this one yet, so. I think that means that the last, oh, well, yeah, we can see it past the last. So, all right. If we, right, because we're using stride, kernel size of 3, padding of 1, right, we're expecting the dimensions to stay the same and the dimensions of the image to stay the same. All right, let's look at average pool. This is just going to be 1-1 because we're basically telling it to average the entire image, the entire tensor, output an average for the entire tensor. So for each feature map, right? So if we have, actually for this, let's do 20. Let's say we have 20 feature maps of size 32 by 32, or of size, I don't know, it doesn't matter, 8 by 8. If we say run average pool over each 8 by 8 feature map with an output size of 1 by 1, then we're just going to take the entire average of that feature map. So we'll have 20 averaged feature maps of size 1 by 1. So to implement that, we'll say output size is a tuple. We'll set self.output size to output size. The kernel height is the h out divided by h in. Where H out is output size 0. I think I have these switched. X dot shape B C N H N W N, right? And then receive the contents of this tuple, and then just divide in divided by H out. That'll be our kernel. And then boom, and then we'll use F dot unfold again. So X unfold. Kernel size equals kernel stride equals, right, and then we make the stride the size of the kernel. So let's say we have a 4x4 image, and we say the kernel size, we want the output size to be 2. Then we'll have a kernel of size 2x2 that takes the average of this, and then it strides over by the size of the kernel, average of this, average here, average here. And that'll output a 1 answer, 2 answer, 3 answer, 4 answer. It'll be a 2x2, right? So in the case of ResNet, and padding is default 0, so we're not even going to mention it, right? So this gives us B do something very similar to max pool. Second dimension. And then we have H out and W out, so we do X mean, so we'll just say out receives X mean dot view B C N H out W out. This should give us 6x20 by 1 by 1 for the expected shape. Output size is not defined. 82. $89. Boom. Done. So that should be our fundamental modules for ResNet 18, and we'll use these to build ResNet 18 blocks. And I think that's all for now. I'm gonna go to the beach. I'm gonna go swim, do some distance swimming. Maybe I'll relax. I don't know. I have strength and conditioning today, so. And then I'll come back later and start building ResNet 18. And then we'll scale it up on RunPod and see if it converges faster in the classification task on CFAR10 than the Vision Transformer, which I think it should, theoretically. So I think it should. Okay, thanks. Questions and comments, and please, any questions, any comments, yes, are all welcome. Thank you.